So this semester we'll be talking about somewhat different topics than the first semester. We'll start talking about electricity and magnetism. And the first few weeks are going to be about introducing what electric charge is. And we will define something called electric field, which is very similar to gravitational field. And we will talk about some very useful tools like Gauss's law, electric potential, and we'll talk about some simple electric devices. So this week, I will not probably be able to finish all of it, but it's like chapter 21, electric charge and electric field. So these are the reading assignments, and these are the suggested problems. So let me first start with like introducing like static electricity and electric charge. And I think the simplest way to show this is to suggest this kind of experiment. I'm pretty sure all of you had this demo in your high school. If you rub a piece of plastic, like a comb here, on like a wool or some sort of fabric, and if you bring it close to pieces of papers, you will see these papers are attracted to the comb. Okay. So if you use somewhat different material than the plastic comb, like not this one, but if you, let's say, use like a glass rod, like say you rub it to a fabric, or if you have hair, you can rub it to your hair and then bring it close, you'll see it also attracts. Then we have to think about different possibilities, right? Maybe, okay, there's like a cartoon picture of this. You can rub two different plastic combs to fabric and see if they attract each other too. Like if this comb is attracting these papers and another comb is attracting the same set of papers, and the question is, how do they attract with each other, interact with each other? Do they attract each other or repel each other? And this is an empirical question. So we can answer this with the experiment. So we can say, like one plastic comb is like hanged like this. We rub it in a wool and then hang it. Another plastic comb is like here, and we can bring one close to the other and see how they react, right? So if this is like a plastic comb, this is like a plastic comb, and if they come closer after rubbing, that means you will, if you do this, you will see that they repel each other. So you can do exactly the same experiment with glass rods, like you hang one glass rod after rubbing, and you bring another glass rod after rubbing, you will see they also repel. Okay. And the interesting question is, suppose you hang one, like say you hang the plastic comb like this after rubbing to a wool, and then you bring a glass rod, right? Let's suppose this is plastic, this is glass. So different from these first two cases, you'll see surprisingly they attract each other. So this one will move like this one, and so basically we have, if you like, three different scenarios of which two are the same. So from this we can actually conjecture the following. So first of all, there are charges. So when you rub plastic or glass on a piece of wool, you create charges, and there are two kinds of charges. One we call positive, the other negative. And from these kind of experiments, we can say, okay, since plastic rubbed to wool, independent of which plastic it is, creates reasonably the same kind of charge, We can say if the charges are like, if it's like a comb, plastic comb, or if this is like a glass and this is a glass, we say it's likely they are the same kind of charges. And since they repel, we say that like charges repel each other. And in the last case here, this guy and this guy, unlike charges attract each other, right? And finally, which is not obvious at all, is total charge is conserved. Like in any system, like for every positive charge, there is an equal amount of opposite charge. So for every negative charge here, if this is like minus, there is like an equal and opposite positive charge somewhere. If it's like the fabric you rubbed, it's probably there. If you use your head hair, it's probably there. But the total charge, this is, I think, the most important thing. The total charge is conserved, and total charge is always zero in the universe, at least at this level. So the question is, where is this charge coming from, right? What is the origin of charge? Maybe when these experiments were first done, like, I don't know, 100 to 200 years ago, people didn't know. I think this was like this was known since like ancient Greece, maybe even before. Like this kind of things were known, but people didn't know the origin. But today we know the origin of charge, and it is its origin is atomic. Basically, the universe is composed of atoms like this, which is like, again, a cartoon picture. And these atoms are modeled like this. There is like a positively charged nucleus. And the nucleus has like both protons and neutrons. Neutrons are uncharged, protons are charged. And circling around this nucleus are negatively charged particles like this. Of course, these are also a cartoon. And we call these charges electrons. And for each atom, they have a lot of electrons, and they have like an outer shell. I think that's called valence shell, something like that. And some atoms hold this outer shell electron very tightly, some don't. So when you put friction on it, like put like hundreds of thousands of millions of these atoms together in a piece of plastic and rub it on against something else, you have a good chance to pull apart some of these electrons. And that's what you see. That's the origin of the charge as we understand today. So the question is, there are two kinds of charges. There's like a positively charged charge and negatively charged charge. So how do they come about, right? And the explanation is, we can only move positive charges, at least on the level of such experiments. And we can only move negatively charged particles, like electrons. And when there is an excess electron in a material, we say it's like negatively charged. When there is some missing electron in another material, we call it positively charged. So positive charge is actually absence of electrons, if you like, which is a reasonable thing. So this is where the charge comes from. The second one is, so where does it go, right? So suppose you did an experiment like this and you had your fun and you come back the next day. If you try to do it again, you'll see it's not there. You have to rub it again and create new set of charges. And the question is, there were some charges on this guy. Where did it go? What happened? And the answer is, of course, it's like complex. There are a lot of possibilities, but most dominant reason is the air. The air here has a lot of atoms and molecules, all kinds of particles, and it has a lot of water like this. And the water is like a funny molecule. It is polar like this, oxygen, and one oxygen and two hydrogens are separated like this. And there's like, if you like, a charge inhomogeneity. Like positive charge is like located around here, negative charge is located around here. We call this like a polar molecule. And when it's like a humid day, these molecules are bouncing around all around in your room outside. And if you have like a column with charge like this, there are like water molecules around it too. And some of them pick up those electrons and they dissipate it into like thin air. And over time, they completely discharge this column. So that's why if it's like a dry day, like I think in seasons when it's not raining, it's like very low humidity, you will notice that there's an excess static electricity in your fabrics. If you have a cat, I'm pretty sure you have seen this. Like in some days, your cat sparkles you more often than others. So, and those are the days when there's no rain and then it's like very dry. So charge, whenever it's created, stays there for a longer period of time. So let me like introduce some terminology then. Like in terms of materials, we have different kind of materials. But to be able to tell you about this, let me probably it's better to introduce some like some toy experiments. Suppose you have like two charged spherical metal balls like this, like one like this, one like that. Actually, let's suppose one is charged like this, the other is neutral. Okay. Somehow you created some charge and you put them on your table and you want to do some experiments now. So one thing you can do is put another metal, like connecting this guy to this guy. Maybe you put like a long nail that touches both of these balls. And what you'll see is initially uncharged sphere, which is this, is going to be charged like this. And initially charged sphere will have less charge. What we say is that charge is moved from here to here through this metal rod or metal nail. And you can do the same experiment with some other material rather than nail. You can, for example, put wood. And what you'll see is no matter how long you wait, the charged ball is charged with the same amount of charge, whereas the uncharged ball is uncharged. So there's no way charges can move from this guy through the wood and come over here. So we call this a metal. A metal means it can conduct electricity. Electrons can flow through it. And we call this an insulator. Electrons cannot go through it. If you put an electron on a piece of wood, like here, it stays there. Has no way of moving. So based on these, I want to introduce these things like metal electrons are freely moving, insulators electrons are tightly bound to like atomic structure there, wherever it is, it stays there. And actually there's like a third kind, what we call semiconductors. And those semiconductors are neither like wood nor like piece of nail, is something in between. And in these semiconductors, there are like free electrons, but not as many as the metal case. So you can think of it like this. If you are in a metal, it's like a, maybe I can draw this. Of course, this is like a cartoon, but to tell you the full story, I have to teach you a lot of stuff. So like quantum and solid state, blah, blah. But here I can tell you some cartoon, like generally electrons behave in a funny way. It's kind of like a bucket filled with water, like this, okay? And this bucket is full with water, right? It's like filled all the way. So, and if you connect another bucket here, I don't know, with some pipe, and you put some excess liquid here, it's going to flow through and then come back to the other one. And the key is, okay, the key is for this to happen, these buckets should have different levels, right? Like suppose this is 1, this is 2, there's like a level difference. And I put like a hole through this. which is this metal layer, thin metal, and then all these excess electrons from this guy will flow into this. Whereas for like insulators, the situation is a little bit different. Insulators, you can still think of buckets like this one, and this one. You can put all the channels and all the tubes you want, but you can't do anything because they are only filled at the bottom. There's nothing to do there. So that's like a cartoon picture of full quantum theory. So if you end up taking any in this future solid state, you'll see this is called Fermi level. And there are so much electrons, you just fill up a Fermi C. This is called Fermi C. And you flow from this C to another C if there's this potential difference. In this case, the potential difference comes from this. Obviously, this guy has like a higher level than this guy. So when you connect, you have to flow, right?
Yes.
But in some cases, you can like, you'll see things like this. In some cases, they can be equally charged. Levels are not different like this, but you have like an electric field. Like there's like a wind blowing in one direction, and this wind will kick out these charges and put it in here. So it can be a little bit different, but we can relate one to. Okay, good question.
Okay, thanks.
All right, let's move on. Now we have charge. We can do more experiments. Let's just think about other experiments. And let's think about metallic objects that we worked with. And suppose you have a neutral metal like this. Like neutral means there's equal amount of positive and negative charges, right? Like neutral means, of course, there are charges everywhere, like plus, plus, plus. Universe is composed of charges, but there's an equal and opposite amount negative everywhere too. Like, I don't know, this is minus. And the key is in the metallic case, like I said, these charges, these guys are free to move, whereas these positive charges are fixed. Now imagine you bring an excess charge close to this metal like this, here. And suppose this excess charge object is positively charged, like plus like this. What this means is there's like missing electrons here, so it's like positively charged. So when you bring this charge, these charge object is going to pull some of the electrons, right? When you touch like this, so these negative electrons here, this one, maybe this one, if this is enough, they are going to move to here. And this initially charged object is going to have less positive charge. And this initially uncharged object is going to be charged because some of the electrons are left. So they are not there anymore, so it's positively charged. So by bringing a charged object to another object, we can charge it by touching like this, like connecting them with like some channel. Now let's think about like a little bit different scenario. We again start with like a neutral rod, the same. And we again bring a positively charged rod, but this time we don't touch it. This time they are separated like this. So there is no way electrons can jump from here to here because there is no channel. Actually, in a higher level, there are some mechanisms, but it's not relevant for this course. They are not touching, but they still can exert force on each other, right? These positively charged ions or particles here can still exert force on the mobile negatively charged objects here. So what will happen is all these negative charges will move in one direction due to this pull from this guy, and they'll leave some positive charge behind. So the metal rod here in total is still uncharged. It's still neutral, but it's like a inhomogeneous system. That one side is charged differently than the other side. There's like a charge separation. Okay. And now let's do one more thing. After we did this right here, let's suppose we connect this to Earth, that we call so-called earthing, grounding. So it's something like this. If you do this, so these excess positive charges here, because they are connected to ground, they can pull electrons and neutralize them like this. And this side is now uncharged, but this other side is negatively charged, right? Of course, unfortunately, this picture is bringing opposite kind of road. I think it would be nice if they kept it, but let's stick with the figures in your book. If you bring a negative charge, this side is positively charged. Initially, this side is negatively charged. And when you ground it, these negative charges neutralized. And let's suppose you cut this ground and you take this rod away, and you end up with a net charge in your initially uncharged system. And the key is you induced this charge on this object by two methods. First, inducing this charge with another external charge, and then connecting it to the ground. Okay? So now I think we can introduce electroscope. Electroscope is like a device that was used to measure amount of charge. And it was actually based on these simple observations I introduced you. It is like a metallic shell like this, and inside this metallic shell there are like two leaves of gold, and these gold leaves are connected through this metallic ball, right? And what you do is, okay, you kind of insulate inside to isolate it from its environment. And the key, okay, this whatever it is, the key here is if you bring like a positive charge here, these electrons in the gold leaf here can move up as a result of the attraction from this positive charge. So the knob here, this ball here will be negatively charged, and these negative charges will leave a positive charge. But since positive charge repels each other, these leaves will separate. So this angle will increase depending amount of the charge. So you can touch it, like you can, this is like induced charge so far. So you can touch this rod, and then these electrons will move, and this whole thing will be charged as a result. And since when you touch, there's like more electrons flowed, and then there's higher charge, so this angle will probably increase. So this is like you charge with induction here, and here you charge with conduction. So here, let's see what they are talking about here. So you can initially have like a charged electroscope. Let's say it's like a negatively charged. And you want to know, like, suppose you know it is negatively charged. Somebody provided that answer for you. And you have like a rod that you want to determine the sign of the charge on this rod. When you bring it up, of course, you know, some of the positive charges will move up, or if you like, some of the electrons will move down, and the bottom part will be more charged, and the angle here will increase. On the other hand, if you bring like another kind of charge, like say positive charge, so what will happen is all these electrons will move up, and total charge here will decrease, so this angle will decrease. This way you can determine, like if you know the charge on your electroscope, hypothetically, you can determine not only the kind of charge on your rod, but also the magnitude, right? Based on these observations. So what happens if I first stop inducing, then cut grounding? Yes, good question. So if, actually I skipped something, but like, let's see. If you first stop inducing and then cut grounding, like my understanding is you just take this away first. If you take this away first, now there's nothing for this guy to be charged, so this is neutralized. And if you cut the ground, you go back to what you started with. It's like uncharged metallic rod. We assume the ground is infinite, like we call it reservoir. It can provide any kind of charge with any amount. So when you connect, if there is like any kind of charge, so suppose you move this guy away, right? And suppose there's some kind of charge, it's positive or negative. But since this ground can provide any kind of charge, it's going to be neutralized. And when you cut it, you just have like a neutralized rod. So because of grounding, there are no less electrons, right? Grounding, like by definition, grounding grounds things. If it's positively charged, it makes it 0. If it's negatively charged, it makes it 0. That's what grounding is. So when you bring a charged object to a non-conductor, these, initially maybe it's like this. Initially it's like this. It's basically 0, like plus and minus everywhere. I don't know how to draw it. But if you bring a charged rod like this here, so what this will do is these electrons, this electron and this electron, they cannot all flow to one end because they are not mobile. But what they can do, they can polarize in local small parts. Like every atom, if you like, here polarizes like this. Another atom here polarizes like this and like this. So if you want, you can think of this case, like in the case of like a non-conductor, we don't charge by induction, but we polarize by induction. So every atom here has like an orientation. Negative atoms are more likely to be on this side than this side, okay? That's like a different case for non-conductors by inducing polarization. So, okay, now I think we are in a position to introduce Coulomb's law, and then we can finish after that, I think. Maybe I have a couple of examples, maybe next time. So, based on all these experiments, and then I think Coulomb did this kind of experiments, you can do all of these more qualitatively. You can do this kind of experiments. I think most of you have seen this setup in the Cavendish experiment to determine the magnitude of gravitational force. It's exactly the same setup, but now rather than having masses, of course there are masses here, but you induce charges and you measure how much it changes depending on the distance and depending on the charge. And I think it was first Coulomb who did these kind of experiments, and he came up with this form. The force, the magnitude of the force is equal to product of the charges here and here, and divided by the inverse square of the distance between them. So another form is, I think we call this like proportionality constant K. But if I think maybe in high school you are used to this, but in this class you may also see this kind. It's like 1/4 pi epsilon 0. And this epsilon 0 is called vacuum permittivity or free space permittivity. It's a property of free space. So since we are talking about force, we have to also decide about the directions, because force is supposed to be a vector, and a vector comes with a direction, right? As well as magnitudes. And the direction is like this. If it's like equal charges, for example, this is like positive, this is positive, force on 1 by 2 is repulsive, so it's on this direction, and force on 2 by 1 is on this direction. If they are negative charges, we have the same thing. Force on 1 by 2 is repulsive on this direction, and force on 2 by 1 repulsive on this direction. And the difference comes when you have like a positive and negative charge like this. So in this case, they are attractive. So force on 1 by 2 is on this direction. So it's trying to come close to the other particle, and this one is on this direction. Okay. So just I have to also mention the units. So the unit of charge here is Coulomb, and this constant, proportionality constant, is something like this. K is equal to 8.99 times 10 to the 9 Newton meter square over Coulomb square. And this unit you can extract from here. So this one is supposed to be Newton. This is supposed to be Coulomb, and meter square. You can find the dimension of K from here. And if you, for example, calculate the force between two charges of 1 Coulomb, maybe you can do this as an exercise. You will see it's like gigantic. It's the kind of force we never see around. And from this we say that generally the charges we talk about in experiments like this are very small, order of 10 to the minus 6 Coulomb, like micro Coulomb scale charges. Okay. So the smallest charge in the nature, which is rather interesting, is this number, like 1.602 10 to the minus 19 Coulomb. There is no way you can get any charge smaller than this. And any other charge is multiple of this. And from, okay, this is the charge of an electron. And electron is one kind of particle with the charge. Another kind is proton. Proton is charge with the opposite. So the convention is electron charge is minus E, proton charge is E. And charge, we call it quantized. Yes, quarks, there are quarks, like for example, if you are looking at the proton, it's formed by so-called up, down, and strange quarks. I think there are like 3 quarks, and each quark is 1/3 of an electron charge. But the key is quarks are not observable. There is no experiment ever done that observed a single quark by itself. Of course, there's like an evidence for the existence of quarks in some experiments, but they don't stay by themselves. They are never seen by, like, there's no way you can find a loner quark with 1/3 of an electron charge. Actually, there's also cases in condensed matter, like there are like so-called anyons, and there are like so-called fractional quantum Hall effect. They also have fractional charges, but it's another story for you. If you're interested, you can take more condensed matter or physics classes in your future classes. So I want to finish this section with like just a little remark. So this form is definitely similar to gravitational force, right? It's also like an inverse score law. It's also like proportional to, so gravitational force was proportional to masses. And here we have charges, but there's like one significant difference, and that's like a very big deal. Gravitational force is always attractive. There is no case where you can get a repulsive gravitational attraction between any kind of thing. But in the electric charge, there are like 2 cases. There's like a case with attractive force, and there's a case with repulsive force. Okay? After Coulomb's experiments, the form of Coulomb's law is like this, right? Force is proportional to some constant K, charge Q1, Q2 divided by the inverse square law, inverse square of the distance. And gravitational force was something like this. I think there was like a gravitational constant, which was also a small number like this, which was very small, unlike this. And we had something like this, M1, M2, again divided by R squared. You can see this is like Q1 goes to M1, Q2 goes to M2, and it's almost similar, right? Which is exactly the same from a mathematical point of view. But the key difference is in gravitation, masses are always positive, right? The mass M1 and M2, any given mass is always positive quantity, whereas charges can be positive or negative. So as a result of this, gravitational force is only attractive, whereas electric force can be attractive or repulsive. There are like charges, like 3 charges on a line, like this Q1, Q2, and Q3, they are given. and we want to calculate the net electrostatic force on particle 3, this guy, due to the other two charges. Okay, what is the net electrostatic force on this guy due to this guy and this guy? So at Coulomb's law experiment case, gravitational force is affecting the experiment. Am I right? That's correct, but we neglect that. Or you can just think of these masses to be fixed, and you just don't fool with any mass. So you just change. So the only change is the charge, of course. But if these guys are charged, there will be a role. Actually, another reason also is like gravitational force is actually much smaller than electric force. That's why I actually want you to calculate this one. If you calculate a quantity like this, you will see there is no way we get any gravitational force that's comparable to electric force. That's also another reason. Good question, thank you. So we are interested in the net force on 3 by other two charges. And there are basically two forces I need to calculate, right? One is this one, force on 3 by 2, force on 3 by 2. And since they are different charges, they repel, they attract each other. And force on 3 by 1, this guy and this guy, since they are the same kind of charges, they repel. So there's like a force like this from this guy, and there's like a force like this from this guy, and we need to sum this up, right? That's the task. So let's do this. Let me try. Force on 3 by 2 is equal to K. So it's like Q2, Q3 over. So this one is, I don't know. Let's call this R1. Let's call this R2. And the distance is R1 squared. And force on 3 by 1 is K Q1 Q3 divided by R1 plus R2 squared. So 8.99 times 10 to the 9 Newton meters squared over Coulomb squared. And Q2 is what? 3 times 10 to the minus 6. Q2. Q3 is minus 4 times 10 to the minus 6. And the distance is 0.04 meters. Right? This is Coulomb squared. So let's check the units. Coulomb squared. So this, okay, this is meters squared. Meters squared. And the result is Newton, as we expect. And this will be what? It's like 100, something like that. So this is F32. Now I want to calculate F31. Similarly, this is 899 times 10 to the 9. 1.5 in the left direction. What about the unit? I'm glad somebody wrote the answer. I thought I was the only one doing this. Thank you for doing this. Good. So times, okay, this is like minus 8 times minus 4 times, okay, 10 to the minus 6 plus 6 is 12. And divided by R1 plus R2 is 0.25 meters squared. Okay, the total unit is going to be, I know now, Newton. Okay, I forgot 0.04 here. So nobody fixed my mistake. I'm kind of disappointed, but that's fine. So I fix my own mistake. 12 times 8.99, it's like 2.6 Newton, something like that. And this one, the other one, 1.15 Newton. So F net is equal to, I think, so F32 minus F31, which is equal to 2.6 minus 1. I think, let's call it 2, 1.45. Yeah, with the digits 1.5 Newton. I found to the left, right? It's in that direction. Yes, good. Great. So I think that's it for me today. There's one more question from your book. I think you can exercise that. And we'll continue with more about Coulomb's law next time.